Hey, QD Coders, this is Michael. Jan should be joining us very shortly, and I expect that we will go through the infrastructure deployment for the Jinaga Replicator as a service. This is a project I'm pretty excited about because this gives front-end developers access to the Jinaga backend without having to set up any infrastructure on their own. They don't even need to run a Docker container. And so I've been testing it out with React Native, and the experience that I want somebody to have is to be able to clone a repository that's a starter kit, and then go up to the Replicator as a service, put in just create a replicator, absolutely free, and then put that URL into the environment file, .env.local, and then they are up and running. They are creating a mobile application that can sign in with Apple, or sign in with Google, depending on which operating system you're targeting, and then use the replicator. Just take the user's information, send it up to my replicator in the cloud, and get things back. So that is going to be pretty exciting. As it currently stands, if a front-end developer wants to create a React Native application, they would need to create a container in their own version of Docker, and then open up access to that container with something like ngrok, and that way the mobile application could connect to the cloud URL and talk to their local replicator. It's kind of a cool thing to see. I enjoyed seeing that working myself, but you know what? That's not the ultimate front-end developer experience, and besides, that doesn't give you the benefits of sign in with Apple, sign in with Google. With the Replicator as a service, when you go up there and you create your replicator, you should be able to say, hey, I'm building a mobile application using React Native, and I want to authenticate on an iPhone. And it says, okay, here is some code. Go ahead and, as a developer, sign in with your Apple ID, and I will configure the application, this replicator, to be a trusted client of that endpoint. So that's going to be a pretty nice experience, I think, and that is what I am striving for. Okay. So it looks like it might be taking on a little bit of time to get away from family and from work, and to join us this morning. I will double check messages real quick and see what if he's happened to send anything. Oh, I do have a comment on EF Core 6 best practices. Hey, that would be a good thing to do some research on. But, okay. So it might be taking on a little bit of time to get here. Let's go ahead and just get started talking about the infrastructure. All right. So I will do a screen share just in case he becomes available, and we can get started. Okay, good. All right. Let me introduce you to the Jinaga Replicator as a service running in Azure. So this is a single resource group that contains all of the components necessary for the Replicator as a service. At the very front, we've got this this portal, this app service that is the user interface, and then that is connecting to this virtual network. And then behind that virtual network, we have this Postgres database. So the portal application is using Jinaga server and making a Postgres connection to do all of its data management. The other resources that you see here are things like application insights, so that I can keep an eye on how things are going up here in the cloud, and various connectors to that virtual network. So we've got things like the private endpoint that the cloud application exposes on that network. And we've got this network interface, which is how that database instance basically adds itself to that private network. And then we've got this DNS zone, so that all of the applications that are running within that private network can find one another by name, and they don't have to reach out to the public infrastructure in order to do that. I got some extremely valuable help from my good friend Sean Weitzel to get this set up. And so yeah, he's an architect at Cloud Architects in Tulsa. So definitely ping him if you have some infrastructure needs that he could help you with. We set all this up with Pulumi. So Pulumi is an infrastructure as code platform. So it's a hosted platform, so that you could go up to pulumi.com and you can see all of the infrastructure updates that you have run. And it's also a command line application that you run on your own machine in order to deploy those infrastructure components. And you keep all the code for that infrastructure in your own Git repository. So this allows for a really great iterative experience for setting up that infrastructure. And then by using a feature that they call stacks, so here we're looking at the dev stack, you can produce new instances of infrastructure. So this entire resource group is controlled by the infrastructure's code, and so if I were to create a new stack, then I would get a brand new resource group with all of these resources recreated over there. And in fact, that's exactly what I did over the weekend. This is something that Sean recommended I do, that in order to test my infrastructure as code to make sure that it actually deploys properly, he recommended that I tear down the dev environment, run the script again to bring it back up. It's a good thing that he recommended that, because I found a few issues that I had fixed manually along the way and no longer worked with the infrastructure's code. So now that I had those fixes in place, I could represent them in code and get the entire infrastructure to be stood up all on its own. So I want to walk through exactly how that all happens. And to start this journey, we are going to go to this repository right here, the Jinaga Replicator as a Service, RaaS. So here I've captured some notes to kind of remind myself of the things that I need to do in order to set up a new stack. The first thing that I need to do is to configure some secrets. So things like the database password for the admin account, as well as the password for the application account. And then the session secret that's used to encrypt the session token that gets set to the browser's cookie. So these are the secrets that I need to set up. And when you run Pulumi config set, then it creates right here a configuration setting in your own repository. So that means pulumi.dev.yaml contains that configuration for the dev stack. Now, wait a minute. What's this? Am I showing you the admin password to my database right now? Am I doxing myself? No, in fact, this is an encrypted password. It's encrypted using a key that I don't even have. I don't know what that key is. That key is maintained at pulumi.com so that I can log in from a different machine. As long as I authenticate with pulumi.com, then this pulumi.com can interpret this encrypted password. So I'm not checking secrets into source control, and I'm keeping everything nice and secure. And I'm also able to work from machine to machine and even share this responsibility with other developers. So we can go up to pulumi.com and we can create an organization. I am not using a paid service right now. This is a free account, and so I cannot invite other people to my organization. But with a paid service, then I'd be able to invite other people to that organization. They could log in, they could get access to the key that was used to sign this password, and then they could run infrastructure updates. So we've got the various secrets in here. The registry password, that's another secret. I did not capture that in the README, but neither is that something that is randomly generated. These are all randomly generated passwords. I want a unique set of credentials for every repository, or for every stack. Then we create the infrastructure by doing a Pulumi up. Pulumi up is pretty exciting. This is kind of the output of it. Let me get a console open so that I can show you what that all looks like. So here is the Pulumi, or the console for the Jinaga Replicator as a service. I can say Pulumi up, and what it's going to do is it's going to compare my current infrastructure as code definition with what I have most recently deployed to Pulumi, or to Azure through Pulumi. And so as it does so, it's going to create a plan for what changes it needs to run. And it says that, oh, I found one change that I need to run. Let's get some details on that change. This is a change to add a new service delegation. This is probably something that that happened because of a Pulumi update or an Azure CLI update. Is that now this this kind of service delegation is required. So as you update the runtime and the tools, then Pulumi will recognize that and then apply those updates to your infrastructure. So it's not just changes that you make; it's changes that that Microsoft makes on Azure. I'm not going to perform that update right now, so I'll just say no. Oh, and in fact, there's already a new update. As of, I just updated this weekend to work on this thing, and there's already a new one. This stuff is changing very quickly. If I take a look through the history up here, I can see all the various updates that I ran. So we can see that some of these are pretty pretty small updates. But if I look at some of the things that I did this weekend, let's see. Yeah, I was hoping to be able to show you some of that history from this weekend, but as it runs an update, it gives you a URL. You can watch the update in real time, and it will do things like deploy new resources like app services, and it will also allow you to set the configuration on those resources. The really powerful the thing that makes using infrastructure as code the best way to write those configurations is the fact that you can set something up once, like for example an admin password, and then you can use that in several different points in the configuration, so you know everything is consistent. And then if you go in and you change your password, as you should roll your passwords every once in a while, you just run these config set Pulumi up, and it'll change the configuration everywhere it needs to be changed. So let's take a look at where it's going to set those configurations. All right, so here we're reading in things from Pulumi config. So for example, here is the admin password. We're going to read in that secret. And then I'm going to use admin password in several different places. So like right here, I'm going to use the admin password in order to create a managed Postgres database. So create a Postgres server and set the administrator login to pgadmin and the login password to admin password. Then from there, I'm going to set up the private endpoint so that it's connected to that virtual network, and then create a database within that server. And you can see right here, I am going to grab the information about that database, like the database name. This is randomly generated every time it runs an update. So we set that database name and load that database name and create a connection string. So now I can take this connection string right here and I can drop that into the configuration as an environment variable inside of my Linux web app. So taking each of the different steps, I can take output from one, use it as input to the next, and I can make things that are nice and consistent. So how does the actual Jinaga database get into that particular database deployment? When we used Pulumi to stand up a brand new database server and to create a new database within that server, it was an empty database. So how do I get my code into it? Well, the way that I had started before doing this weekend was that I exposed that database endpoint to the public, added a firewall rule so that my machine could get to it, and then logged in using the administrator password, which I grabbed so that I could see it. And then I ran the migrations. But that's not repeatable. I want this to be completely repeatable. And so I created a container that runs the migrations, and then using Azure Container Instances, I deploy an instance of of the image that I upload to the registry, and it runs those migrations. So here's the migrations container, and here is where I give it the admin connection string. So this is the connection string that contains that that secret that was generated and used to create the Postgres database, the Postgres server. And then I also give it the application password, because this migrations image actually creates the application user for me. So it sets everything up so that the application can start running. So using this, I pull from Jinaga apps.azure.cr.io. That's the Azure Container Registry. So I can set up my own registry, and I can upload images to that registry. And so this is the image that I want to use, the RaaS migrations 1.1.3. So now, anytime I need to change the migrations in any way, I can just come up here and go to the scripts and say, hey, I've got a brand new table. So here's the fact type table, here's the role table. I'm going to create some kind of a new table, and then put the script in there. And then I can run this Docker file, create a new image, and I will call this 1.1.4. Or if this is a really new change, I might call it 1.2. So I will create a new image, and this image will contain this script to run the migrations. So it's grabbing the Jinaga admin connection string as an environment variable. It's using the Jinaga app password to change the password of the Jinaga user, the application user. And it's running all of these scripts. So I upload a new version of that image. I change this this file here, and then when I come over here and say that I want to Pulumi up, then it's going to recognize, hey, you're trying to deploy a new version of that image. That means that I'm going to need to take down that container instance and start up a brand new container instance. And then as it does so here it's saying, okay, I'm going to replace migrations.dev. If I take a look at the details, it's going to replace, it's not actually showing what changed within the, I was hoping that it would show the tag that changed from this to this, but that's the reason that it's that it has done this, is to say that I'm going to tear down one container and set up a new container. Here it doesn't actually have the secret to compare, so it thinks, okay, there may be a change in the secret as well, but I'm not sure if that's actually true. Anyway. The important thing is that doing this gives me a way to update the database as I'm working on the application, and I never have to expose that database to the public. I can just run all the migrations up in Azure. So this is a pattern that I've used in professional development, but this is the first time that I've ever been able to use this for a personal project, and I think it works really well. It's a little bit more work to set up, but once you've got this, then you've got that really quick developer experience. So what I do as an individual developer is I'll make the changes to the setup scripts, and then I will build this container and then just or build this image and then run a container locally, just using -i-t. So interactive and then terminate. So I can see everything it's doing, and then it goes away. And once I've got the iterated on that, and I see that it's doing the right thing locally, then I can upgrade the number and push it. You can see here I've set the restart policy to never. Azure Container Instances are intended to run workloads, and so you should be able to set the restart policy so that when it terminates, it restarts the container. But in this case, the intent is for it to terminate. Now, there was one thing that that really kind of messed with me a bit, and that is that as soon as a container instance terminates, you can no longer see the logs. Let me show you what I mean. Let's go up here and let's take a look at this. So that's the database itself. Here is the container instance for the migrations. Now you can see the containers inside of that container group, and we can see that the migrations, the RaaS migrations, has terminated. Nothing is running. Because we set the restart policy to never, we only have one run, and that run was on 3/18. If I try to look at the logs, I can see the logs for that run. Before working on it this weekend, I was not able to see those logs. And the reason is that it terminated too quickly, and Azure did not have time to collect those logs. So now it's waiting. It's doing this pausing for inspection. There's actually a line right here inside of try sh to sleep for 1 hour. So when it runs the migrations, then I come up here, I'll actually see that the current state is running. I'll be able to see the logs. I'll see everything that it has done, and that gives me any errors that happened. That gives me a chance to monitor and to respond. But then once I'm convinced that everything was working properly, then I can just come up here and stop the container group. And if I forget to stop the container group, it's going to terminate in an hour anyway. So I won't be spending any extra money on a migrator that's already done its job. So that's the pattern I'm using for running the database migrations in Azure. This migrations container is connecting to the private network, so I never have to expose the database outside of that private network. Okay. Yeah, so this has really been a powerful tool for building and iterating on the Replicator as a service. This set of resources is going to grow very soon because what I'm working on right now is a central hub replicator. So that's going to be another app service that's running inside of that VNet, and that central hub replicator is what the portal is going to push all of its facts into, and then others can connect to that central hub. Other things like some Azure functions that will set up the API routing and rate limiting and those sorts of things for the replicators that people set up through the portal. So I'll have a bunch of functions. Each of them will connect to that central hub, and then they'll be able to see what work they need to do, report back that the work has been done, and then that information will flow back to the portal, and everything will just kind of flow through. So as this progresses, I will definitely share that topology with you. Now, one other thing I want to show. Let's go to dev.jinaga.com. Let's actually take a look at the Replicator as a service. Now, I have demonstrated dev.jinaga.com on this channel in the past few weeks, and you saw that I had created some replicators. Now I don't have a replicator. Well, that's because I tore down the dev environment. I didn't bother to back up the dev database. I just blew it away, and then created the dev environment all over again. So none of my replicators survived, but that's okay. I know that I've got several different options for preserving the data. Some of them are just using backups in Azure, but another option is to connect replicators together so that one of them pushes its changes into another, and I'll have a hot backup. So doing that kind of mechanism, I'll be able to preserve the data once it becomes important to do so. At any rate, I do not yet have a replicator, so let's go ahead and create a new one. And so this one, we are going to create a replicator for the application Monster Hotel. And let's go ahead and create this as a developer replicator first, our development. So that way I can start building my my application in Monster Hotel, and then run this replicator locally. And so then I just copy this and I paste it into .dev.local, and I start building my application. Then I come back up here and I say, all right, now it's time to deploy Monster Hotel to test flight. So I set up a replicator for the test instance, and now I copy this and I paste that into my CI/CD secrets for deploying to test. All right, so now all of my testers are using a different replicator than I used for local development. Then when I'm truly ready, let's go to production. So let's deploy Monster Hotel to production. And now I've got my production replicator instance. So that's the idea of creating multiple replicators. So they're each their own separate database, and they're each their own separate endpoint. Now, what is really cool, some things that that I changed during the course of getting this to work well, is that I changed the way that the network communication takes effect. So let me switch to showing you the network, and I want to let me show you the overview. And yes, and now we'll be able to see kind of the flow of requests as they come in. All right, so let's refresh this, and okay, let's not preserve the log so that we can actually see what's going on. Oh wait, okay, it's not the overview that I'm concerned with, it's actually this right here. So let me turn off that overview, and let's take a closer look at what's happening when the Jinaga client talks to the Jinaga service. Okay. So, when we first load the page, the thing that we are looking for are the feeds. Let's see if I can get a nice clean waterfall. This one looks like it's, oh wait, yeah, I sorted it by the wrong thing. Come on, just. Yeah, I don't want to sort by name anymore. Sort by waterfall. Okay, that's it. Yeah, there we go. So the very first thing that it does, well, after it logs in, of course, is that it fetches the feeds. So this is the specification for the first query that the application runs. So as an application developer, I didn't write this specification language. I wrote using JavaScript. I used the TypeScript types. I used the Fluent syntax and built a specification. The user logged in. When they did so, you can see that that gave me back a user fact, and that user fact has a particular hash, SWV. So then when I requested the feeds, I said, let's start from that particular hash. I just passed that fact in, and it pulled the hash and created this specification. So now it's looking for the, starting from that user, give me all of the user names such that the user name, the name arrow user, so the name points to that particular user that I passed in, that parameter. And then just project out that one single fact, the username fact. So that is what the code asked for. That got turned into to this specification language and sent up to the server. And the server responded with a collection of feeds. In this case, just one feed. This feed SUZ. We can see that feed showing up right here. What that is a collection of tuples, and so it's pulling tuples from that feed, just the same way that you would pull blog posts from an RSS feed. It's the same kind of idea. So we are asking for those feeds for that particular specification. Meanwhile, the application continues to load, and it runs a few additional queries. So this here is another part of the application that is running a very similar looking query, but in this case it's looking to project just u1.value. So that would be this control right here that is just showing the user's name. Meanwhile here, this part of the application is running a much more complex query. So starting from that same logged in user, let's look for replicators, such that the replicator's user is the logged in user, and there does not exist a replicator deleted. So these are all the replicators that I've created and have not deleted. And then from there, I want to project the environments. So show me the replicator environment facts related to that replicator, such that there does not exist a next environment, the mutable property pattern. Also project out the hash, the identifier of that replicator, and then another mutable property, the names. So show me all of the names, the application names that have been created, and project out their values. So when I run that one, that's a much more complicated specification. It's going to produce more feeds. When I look at the response, let's preview that response. Excuse me. I see that that produces these 6 feeds. So each of the feeds refers to a different part of the specification. One of them is just getting all of the replicators that exist. So it's running the not exist clause within the feed. But then that means that you would never learn about the deletions of those replicators if they're removed from the feed. So therefore, there's another feed that shows you just the deletions. Of course, that will never return the ones that have not been deleted. So you need both of those in order to complete this part of the specification. But then, going into this, this environments, it needs to produce another pair of feeds, all of the replicator environments, and then all of the successors that have replaced them, so that the predecessor no longer exists. So that's another pair of feeds, and then a similar pair for names, giving us a total of 6 feeds that are necessary in order to completely flesh out this, the results of this specification. So, if we go back to the waterfall, we will see that we have asked for the feeds for logging in as the user, and then the feeds for updating these parts of the user interface at pretty much the same time. But we didn't wait for the results to come back for those to complete. And then in this case, we got back that we needed the SUZ feed, because that was what was returned from this very first one, and said, okay, let's go ahead and fetch from that feed. And that fetches the the set of bookmark, or the set of tuples. So the things that we are looking for are just the username, so that's the only thing in the tuple. So let's get back the reference for that username. Meanwhile, these other two have finished, and so now it is starting to pull from those feeds. Now, the optimization that I made just recently is that this one here is saying I need the SUZ feed, and this one here also said the same thing. So by the time it finished, it recognized, oh, that feed is already in process. I'm not going to start a new fetch from that feed. So we do see later on a fetch from that feed, but that is because this one returned a bookmark, and we need to go back and see, is there anything more past that bookmark? But before that optimization, it would actually send this request with the initial empty bookmark starting from the beginning. It would send that twice. So that was a good optimization. Furthermore, and this example doesn't really demonstrate it quite as nicely as some of the other examples I was testing with, but this one here, this returned some feeds that if we had another specification that was starting at roughly the same time, there might be some overlap. So the system is actually going to wait until the specifications that started at roughly the same time have all finished, and then it's going to say, give me just the unique set of feeds, and start them all at the same time. So you can see all of these starting at the same time, and it's not because this one thing ended and then immediately kicked them all off. It's because there was nothing else. There were no other feeds requests waiting. So this is actually the optimal shape for fetching that data. This is the best that we can expect. So I was very pleased to see this kind of structure starting to emerge. So in each one of these, we start to fetch from some feeds, and it says, oh, okay, this one's empty. This was probably the deletion, if I were to guess. In fact, I don't have to, well, yeah, I do have to guess, because it's obscured behind this hash of the specification. The server knows what that specification means, but it's now been obscured. The client doesn't know. This one here, we are getting a set of replicators. So this is that very first one. So these are the replicators that have not been deleted. We have 3. This one here is getting probably the yeah, that one's also coming back empty. Yeah, so this might be successors of names, successors of environments. One of those where not exists. In fact, we can go ahead and change something, and we'll see that that take effect. This one here, we can see it's getting all of the environments for all of the replicators. So the same 3 replicators as we got from the previous feed, plus their environment configurations. So you can see there's a little bit of duplication of information coming back. This this 1IV, that was also returned from here. So those same 3 replicators are returned. But yeah, this specification asked for more information in its tuple, and so you got that additional information. This hooks them up. This lets you know, oh, this one goes with this one. These are consistent. And you might be concerned about this duplicate data coming back. Is that something that can be optimized out? Not to worry. We will get to that in just a second. Meanwhile, we've got the changes to name and the current names themselves. So there's the 1IV again, and its current name. So all of these fact references come back, and then as soon as we have all of the results of these feeds, then we kick off a load. So that load starts when the last fetch from the feeds terminates. So it's caching all of that up. It says, I know all of these are in progress at the same time, and they're all part of the same group that started at the same time. So I'm going to wait until they terminate. Before making this optimization, it did load after each individual one, and so that was a lot of additional latency. Plus, it wasn't able to take advantage of removing those duplicates that came back from the feed requests. This load right here, you'll notice, is starting as soon as this feed finishes. Let's see, this one? You know what? Actually, I think this is demonstrating something else that's happening. Yeah, this is another important optimization, or an important part of that optimization is that this here. Let's take a look at how long it took to run this. So yeah, it actually took 177 milliseconds to run this. So rather than just strictly waiting for the slowest one to return, it's actually going to batch things up, and then after 100 milliseconds, it's going to say, all right, let's go ahead and load what we have. And then we can continue to wait for the others. So this actually started 100 milliseconds after the first bit of information that I got back. So if you were to compare the end of this green line with the beginning of that green line, that would be a 100 millisecond delay. So now this one, it's saying, all right, what I have so far is I just have this user name. So go ahead and load that one in. It hasn't received any of the replicator IDs by this point. So, so that gives me back the username, and it does the transitive closure so I can see what the user itself was. And then I have all of the values of those fields. So that's all loaded into memory. But then this load, you can see this is the one that begins as soon as that one ends. So we started the 100 millisecond timer over again as soon as we get some more stuff. So that would be that green line starts it again. But then this occurs less than 100 milliseconds later. So it says, all right, I've got everything. Well, let's go ahead and load the rest. So now in the payload, you can see that it's asking for these 3 replicators. So there's the 1 IV, but it's not repeating that. These are different replicators that it's asking for. And then it's also saying, okay, I learned about these names, so load those in. I learned about these environments, load those in. Give me everything you've got related to that. And then it puts together a response that is just the transitive closure of those particular facts, those 9 references. It says, okay, the replicators that you asked for, they happen to be the predecessors of these 3 names and these 3 environments, so I'm not going to repeat them. But in addition, this user, which you didn't ask for, but I know in order for you to truly understand what's happening, you need to know about this. This user is the predecessor of all of those, so it gives you that complete transitive closure. And so that comes back nice and quickly. And then we have we've fetched a bunch of information. Will you go ahead and update the user interface by running query inverses and putting that information into the right place? And then we come back and say, all right, when you returned, you also gave me back a bookmark. 10.9 was the bookmark here. This one was empty because there was nothing returned. 11.9, 9, and it's not a coincidence that they all ended in 9 and 2. So these are the bookmarks that if you were to fetch from this feed again, you would just say, start from that bookmark, start from bookmark 2, start from bookmark 9, or from 10.9, 11.9. And those are actually part of the payload. Those are the query string parameter, B. And so these fetches that occurred here, these were additional loads to the server to say, are there any new facts that I don't yet know about? Are you batching information as it comes back to me? And then once we've confirmed that all of this information is here, then we go ahead and dismiss the loading loading behavior and show that to the user. So that means we get this nice fast, boom, solid behavior, and if everything is still up and running as quickly as it can be, then it gets all this from cache, and you get a nice fast experience. When you drill in, then excuse me, it's going to be able to display that user interface from the information that has already been loaded onto that machine. And since it knows that I've already run that particular specification, it knows that it can just go ahead and display that without showing any loading indicator. Each of these has been displayed in the past, so we don't have that loading indicator. We do see that it is going back to the server just in case, just doing a quick refresh. But the experience that the user sees is pretty much an immediate response. Now you might have noticed, I'm trying to see if it shows up again, you might have noticed that sometimes it does flash a little bit up here in the title. And that's just the amount of time that it takes for Jinaga to run the specification in memory against the cached facts and then update React. So that is not waiting for the response to come back from the server. But if the server does say, hey, there's new stuff, and then updates it, then it will tell React to update everything. So got this tightened down to a really solid user experience, and optimized the waterfall so that we get the best possible shape for all of these fetches. They happen in parallel when they can. They don't happen any earlier than they need to, and they don't happen any later than they need to. So here we're not going to wait until we get the information back. We're going to go ahead and start it right now, because that's 100 milliseconds. We're not going to wait any longer. But something comes in a little bit later, and then we'll say, okay, now let's go ahead and kick off another load at that point. So it self-optimizes. It's a solid experience, and the really nice thing is, as an application developer, I don't need to set up an API and think about how I'm going to refresh my cache from that API. All of that is built from the specification language itself. So I'm pretty pleased with how this is all turning out. I've got a nice developer experience to deploy these Azure resources, and a good experience for the end user as they are using these Azure resources. So in the future, people will be able to use these replicators to build their own applications, and then just use their front-end development skills, and not have to worry about databases, APIs, or any of that. They just create a replicator, copy a URL, and go. That's the vision. That's the dream. So I hope that you'll stay with me and follow along and test this out. Right now, if you were to copy this URL and actually try it, it doesn't do anything. But when this URL is actually running a replicator, I will definitely let you know. And I want you to build an application using the Jinaga Replicator as a service, and tell me how that worked for you. I hope that it's going to be a delightful experience, and I really look forward to bringing that to you. So, in the meantime, I've been Michael L. Perry. Check back next week, and we will talk about the next advancements in the Replicator as a service. Maybe that central hub will be up and running. So that would be quite a nice little thing to demonstrate. But until then, I will talk to you next week. Thank you very much.